This lesson is on Doppler effect. You may have watched the EH physics video already, which gave you a little intro on the overall concept. So you can think about the diagrams that I drew when I did the mock speed lesson, or think about the ones you just saw in that video. And you saw the wave fronts were different depending on the speed. So Doppler effect is the effect that relative motion between an observer and the source of a sound that causes a change in the frequency. Moving toward each other leads to an increase in frequency. Moving away from each other, a decrease in frequency. So down here, this is sound emitted from a stationary object. So something that's stationary, right? So we get the rings that are concentric, and they're just going outwards. So no matter where we're standing, the frequency is going to be the same, right? Think about it as the frequency is related to the wavelength. So these distances between here, it doesn't matter if I'm on that side or if I'm over here, they're the same. Granted, my drawing's not super, but you get the right idea. So the frequency is going to be the same regardless of where I'm standing compared to where the sound is being created. Now, in this one over here, we have motion. And when you have motion, you cause the wavelength, the wavefronts to change, right? Because they're being emitted from different spots. So now, if I'm the observer over here, okay, so if I'm some person listening, draw a little Mickey Mouse there, got some ears. So I'm over here listening. Well, these wavefronts are now really close together. So this frequency is going to increase. Okay, the wavefronts got, the wavelength is shorter, so the frequency must increase. And if I'm an observer on the other side, well, then I've got these really long wavelengths on this side. So that means the frequency is decreased. So it all depends on where you're standing relative to this motion. There's an equation to describe this phenomenon. And the one in your book, Mr. Owikawa and I talked about, and we don't like that one. The one you see here is the more commonly used one. They will result in answers that are really close to the answers the other equation would give you, but not the same ones. And from what we know, this is the accepted equation. So we're going to be using this one. So the frequency that the observer hears will be a ratio of the speed. So the speed of sound over the speed of sound, either plus or minus the relative speed between the object that's emitting and the person that's hearing. And that's multiplied by the emitted frequency. So this whether it's plus or minus depends on whether you're going toward or away from the object. So we'll do an example. A police car approaches at a speed of 20.0 meters per second, with its siren emitting a frequency of 1.0 kilohertz. What frequency does a stationary observer detect? The speed of sound is 330 meters per second. So I've listed the given and requireds here. So the speed of this object is 20 meters per second. So we didn't actually have to do any calculating to get the relative speed, because we're going to observe, we know that this observer is stationary, right? So stationary means that whatever speed this has is going to be the relative speed. If the observer was moving, then we'd have to do some calculation. But in this case, the relative speed is 20 meters per second. The emitted frequency is 1 kilohertz, and the speed of sound 330 meters per second. All right, so I'm going to write out our equation here. So the observed frequency will be Bs over Vs, and now I have to figure out if it's going to be minus or plus. Well, we know that if it's going toward the observer, that the frequency is going to increase, So that means we need the denominator to decrease so that we're getting a number bigger. So when they're going toward, we use minus the relative speed. Okay, so we've chosen the minus here because they're going toward. If it was away from, then we would use plus. And that's times the emitted frequency. So the observed is 330 meters per second over 330 minus 20.0 meters per second times 1.0 kilohertz. Now you see that as long as we're using the speeds in the same unit, it doesn't actually matter what unit they're in, as long as it's the same one, because meters per second divided by meters per second yields nothing. So as long as we're using the same unit there, we're fine. And the frequency, again, it doesn't matter what unit we use. Whatever you use is what you get out at the end. So now I need to actually do this calculation here. So I'm going to pull out my calculator. So I'm doing 330 divided by 310. And I get a number that's close to 1. It's 1.06 approximately. And times 1 kilohertz. So we get 1.1 when we round kilohertz. Therefore, the observer hears the siren at 1.1 kilohertz.